Hi, this lecture is about chapter 14, Introduction to Inference. So, we are going to cover some of the concepts like confidence interval and how to derive p value, how to do statistical testing, so significance test as an example. So, let's dive into first question. That's about calculating confidence interval, A part. So, it says the 19 deer mice described in previous exercise. You can refer in the textbook, Baldi and Murray, this one for the previous example. So 14 deer mice, right away we know that n, that's the sample, is 14, had an average body length of this much. So that's our mean body length, so x bar. Assume that the standard deviation of body length in the population of all deer mice is rich in the rich forest habitat is the same as mu, that is the population mean, sigma, that's 8 millimeter for general deer mouse population. Okay, so we know x bar, we know mu, we know n, right? And we have been asked to calculate 90% confidence interval for the mean body length of all deer mice in forest habitats, right? So here's the formula for confidence interval. So confidence interval is equal to x bar, that's the mean of sample, plus minus, because we know it's an interval, so it has got some lower boundaries as well as positive, that's determined by that much margin of error. So this is nothing but plus minus margin of error, that's nothing but z critical or z star, you can say, times sigma over square root of n, right? That's the standard deviation for sampling distribution. So we know here x bar is given 91.1, we know sigma, that's 8, we know n, that's 14. We don't know direct value of z star in this case, but we do know that we have been asked to calculate 90% confidence interval. So based on that 90% confidence interval information, we can derive the z value. How to do that? That we can do it by using table C. So let me show you table C. That's the confidence interval table, or whatever you call it. So this is table C, confidence levels, and we can just look at 90% confidence interval, and we'll just look for the corresponding z value. So go all the way to the bottom till you hit the z-score. See, this is the z star, and if you go there, you can see that z is 1.645 for 90% confidence interval. So just plug that number in there and then it should be easy. So 1.645 is your z. You got it, 1.645. We got it from table C. Just plug that in number. So confidence interval is equal to mean, that's this, plus minus z times sigma over square root of n, so basically 8 over square root of 14. If you solve that, you should be able to get 2.138, and if you further solve that math, you are going to get the two values, because on one time it's going to be addition to mean and on other time it's going to be subtraction to mean, right? So it's going to be 91.1 plus minus 3.57. So 91.1 plus 3.57, that should be 94.6, and the lower bound would be 91.1 minus 3.57, that is 87.6. So you can write in a very well known convention of confidence interval. So 95% confidence interval, in the parenthesis lower boundary 87.6 comma the upper boundary, that is 94.6. That's what your final answer is. So pretty simple. Then let's look at the question B. That's a subtype of the same question. So this confidence interval is shorter than your interval from the previous exercise. So we are not showing the previous exercise here, but in the previous exercise we might have looked at 95% confidence interval instead of 90%, as in this particular example. And it says, even though the interval comes from the same sample, why does the second interval have the smaller margin of error? So margin of error is this part. So basically, if the margin of error is smaller, that means you're going to have like less variation, or the range would be, or the interval will be smaller, right, or narrower. So with 90% confidence interval, we got our interval as 87.6, something like this, to 94.6. And we can imagine that the 95% confidence interval, the interval with lower and upper boundaries would be further away. That means the total interval would be wider than the 90% confidence interval. And we can certainly see that there is a precision and accuracy issues with considering either of these confidence interval. So it's just like the cost effectiveness, we have to deal with that. But to testify whether why would we get narrower confidence interval with smaller confidence interval value, and why would we get broader confidence interval with the larger confidence interval formula? Mathematically, you can, if you look at the confidence interval, that's nothing but x bar plus minus z star times this, right? Standard deviation or square root of n. So if we are looking for the same sample size, this remains same, this remains same, this remains same as well. So the only thing which changes is z star for 95% and 90%, right? So you can actually see that we already calculate, we just referred that z value from table C. For 90%, it was 1.645. So at that time, you were just multiplying by that much, right? But if you look at 90% confidence interval by using the same table, 95% confidence interval, go all the way that is 1.960, right? So your multiplier in that case is different mathematically for 95% 1.96 something. That's for 95%, that's for 90%, right? So definitely, if you have larger value here, and then you will have sigma over square root of n, that's x remains same, that's everything else remains same, right? Sigma over square root. So you can see that if you have the larger number, this margin of error has to be larger. If you have smaller number, 1.6 is smaller than 1.9, so definitely your margin of error is going to be small. So if margin of error is smaller, that means you know that if this is the mean that we are referring to, this is the margin of error negative, margin of error positive. So we know that our margin of error is narrower or smaller, so we have the narrower interval. Similarly, if we have the margin of error larger, m is larger, then we have larger interval, right? So that's what we have to look in here. And we can also think about the accuracy and precision, what we could get by selecting either of these. So we can get shorter, that means more precise, right? So this is more precise because it's shorter. So you get more precision with this shorter confidence interval or smaller confidence interval level, whichever way you like to call it. But this comes with the cost of less accuracy. So downside is it's less accurate because we are only 90% confidence. In other words, we anticipate 10% of error, or alpha level is 10%. And we are going to see that alpha is type 1 error a little bit later, right? So our cost in this case is less accuracy. If we go for 90% confidence interval, that's a narrower confidence level than the 95, but our benefit would be more precision because it's a narrow one. So similarly, you can think about this 95% confidence interval. If you are going for 95% confidence level, then you are more confident, right? So you're 95% confidence. So that means you are more accurate because your alpha is simply that error 5%. So alpha is 5%. So you're more accurate in that case. But again, the downside would be that you lack precision because you're saying that this mean could be anywhere between 80 to 100. So basically you don't have the precision when you say that. So that's the cost, and it's always there in statistics. You have to choose based on your research interest which one you should go for. So that's the individual decision that we have to make, accounting for the cost. So now let's look at this second question. According to US Department of Agriculture, cartons of 12 large eggs should have a minimum weight of 24 ounces. There's an average egg weight of that's an average egg weight of 2 ounces or more per egg. So you suspect that certain products of producer sells eggs of inferior caliber. That means they are selling eggs of lower weight per egg or something like that in its carton labeled as large eggs. So when they label it large but their weight is lower, that means their quality is inferior. So in that case, how would we state our null and alternative hypothesis for a test to assess your decision? That means we have to comment about, we have to assess the quality of the eggs, right? So state what parameter mu you would think in in stating this hypothesis. So we can certainly see that we have to compare the weight of eggs. So we can say that our null hypothesis is weight of eggs or average, because we are saying that this is the mean. This is just a mu, not mu r. Let me just write it again. So that's mu equal to 2 ounces per egg, right? That should be the standard, but we are hypothesizing, or we are suspecting that certain producer might have inferior quality. That means it might have weight which is smaller than the standard criteria. That's why our alternative hypothesis would be mu less than 2 ounces per egg, right? So that's how you state the null and alternative hypothesis. And from these null and alternative hypotheses that you have stated, you can easily see that it's a one-tail hypothesis, because you are just not bothered if it's more than 2 ounces per egg weight, then you are not bothered. So you are only looking at one particular tail of probabilities when you consider that. So if this is mu, if it is less than 2 point or not, so that's the one tail that you will be looking for, not the two tails. Now let's look at the next question. That's about p-value. So this is more theoretical question. When asked to explain the meaning of p-value, the p-value was 0.03. The student says that this means there is only probability 0.03 that the null hypothesis is true. Is this an essentially correct explanation? And explain why. So I don't think it's a right answer, because it's just saying that this is the probability that the null hypothesis is true. So answer is no. Why? Because P is 0.03 does not mean that the null is unlikely, but it only in the sense that the evidence would not occur often, very often, if the null were true. So I wanted to take you to the interpretation of p-value with an example before we dive. Otherwise, you will find it a little bit theoretical. So let's look at this example here to illustrate the p-value interpretation. So let's look at the phosphorus level for some population that vary normally. So we know that one of the assumptions is made, standard deviation is given sigma. So second assumption is given to 0.1. Null hypothesis is mu equal 1.2 and alternative is mu less than 1.2. So we are stating or hypothesizing that the phosphorus level is lower than there in the population. So the mean phosphorus level from 12 elderly subject is 1.128. So we got it from these 12 samples, and that's why we are probably hypothesizing that even for entire population of elderly people, it should be less than 1.2, which is for in general all population. So what is the probability of drawing a random sample like this one with a mean value as small as this one or even smaller? So you can see that this particular mean value is smaller than the population parameter, right? 1.2. 1.12 is smaller than 1.2. So if null is true, actually that's the answer for this is nothing but the p-value. So p-value is the probability of drawing random sample with mean as small as this one or even further smaller, because all the alternative, basically we are favoring the alternative hypothesis if in reality null is true. So in other words, is the probability. So I'll just read this definition. It's a book definition. I'll read it in this fashion. So p-value is the probability of obtaining sample statistics at least as extreme. This is the extreme that we are talking about. At least as extreme in the direction of alternative hypothesis as the one obtained if null was true. That's the reality. So we are saying that what is the probability of getting a result by chance alone? Why it is chance alone? Because in reality this is true and we only got this result as from this sample merely by chance alone. That is the probability that we are talking about, and we want it to be as small as possible to prove that we favor alternative hypothesis. So again, p-value is the probability of obtaining statistical sample at least as extreme in the direction of alternative hypothesis as the one obtained if the null is true, if this is true. So later on you could also think about this in similar context, that it's the probability of getting the results. Look at the pointer, getting the results due to chance alone, right? Because we say this is when this is true, when null is true, we got this result. That means we got the results by chance alone. That's the probability. So that answers that hopefully help you to interpret this correctly. So P is a probability associated with sample. That's the another clue. It's the probability associated with sample and not with the hypothesis. So either null is true or isn't is a probability associated with sample. Right? And they were talking about the hypothesis. So So that's like the p-value interpretation. Go back and read again if you get confused, but that's certainly very important concept. So now let's look at implication of this p-value by solving some of these problems. So IQ test scores, example, previous example 14.3 gives us IQ test score of 31 7th grade girls in Midwest school district. That's mean our N is 31 girls. IQ score follows a normal distribution. So our first assumption is met here with standard deviation sigma. So our second assumption is met here. Sigma is known. We are also going to look at some method to deal with such kind of questions when the sigma is not given to us in the next chapter. But as of now, sigma is given to us, second assumption is met. Treat these 31 girls as simple random sample, so even our third assumption to solve these problems is met here. IQ tests in a broad population were supposed to have mean of 100. Is there evidence that mean in this district differs from 100? So that's the key question here. And we have been asked to follow 4-step process to illustrate that. And from previous example, we got the mean for sample as 105.84. So 4-step process means you just have to answer the question by stating a problem, stating plan, solving the proposed plan, and then concluding your answer as a final step. So these are the 4 steps. So you have to write these steps if it's been asked to solve in this particular fashion. So first thing is stating a problem. So you can read that, is there an evidence that the mean in this district differs from 100? So our question, research question in this case is, does the mean IQ differs from 100? So we have stated our problem here. So in the plan part, we just have to explain what is going to be your plan. So we know that dealing with this kind of problems, we have to make some assumptions, or we have to rather state hypothesis and two mutually exclusive hypotheses, null as well as alternative, and we would just favor one over other so that we will reject the other one. So null hypothesis, that means null means there is no change or no association. You can think along that line, because the hypotheses are going to change based on the type of interest. For this particular question, we are comparing the mean, or we are just looking at the mean. That's why our null says mean does not differ. That means mu equals to 100, what is being proposed in here. And the alternative is mu does differ from 100. So that means mu not equal to 100. And based on the question of our interest, we just do not care about whether it's less than 100 or is it greater than 100. So basically we just have to see whether it differs from 100 or not. In that also means it's a two-sided test, right? Because if this is the distribution, we want to look at whether the mu would be on either of these sides. So that's a two-sided test, z-test. So to solve this problem, we know we just do the significance testing for these hypotheses, and we can either make use of p-value or confidence interval or both, and conclude based on those values whether one of these is true. For this question, we just have to see if it differs or not. So we can just make use of p-value and we should be able to answer our question. The simple process I wanted to take you through is, this is how the X distribution looks like, and definitely this is the two-sided test. So we'll have to look at the two different tells, but just the standard protocol, transform the X distribution to Z distribution, and then from that Z values, this will be plus Z, this is negative Z. So from that z value, we are going to use either table B or C to get the p value. Once we get the p value, we can compare that with significance levels. So p versus alpha, that's our significance level. We are going to compare that, and based on that, we can say whether the test is significant or not. In other words, we favor oops, favor null or alternative, or do we reject null or alternative hypothesis? So we can conclude based on the result. So this is how the entire plan looks like as a big picture, and now we are going to solve it step by step. So we know to transform the x to the z score, we have this formula. Z is nothing but mean of sample minus population mean upon sigma over square root of n. Don't get confused with this mean x bar stated here. In a couple of chapters earlier, we used to look at x value, some x value, because we were particularly looking at that particular x score. But here we are comparing the means. That's why we are comparing the mean with the sample mean. That is why we are putting x bar in this case, and we'll be looking at this z score. So in that particular formula, you just substitute the value. X bar is 105.84 given to us. That's given. Mu is 100. That's what we are testing. Sigma is 15 given to us. Sigma and n is 31. So just substitute that value and get the z value. You should be able to get the z value as 2.17. So once you got that z value, now there are two methods. You can either use table B or use table C. Simplest is step 2, but I just wanted to show you both the steps. So using table B, we look at table B always give us value on the left side of the Z. So if this is the Z that we are looking at, it will give us this, but we are interested in tails, actually two tails, but for a moment just look at this one tail. So if we want to get this tail, we want to find the probability for Z and subtract that from 1. So let's find the probability 2.17 using table B. So this is table B, Z 2.1, and this is 2.17, that's 0.9850. But that gives us this horizontal bar, shaded area, shaded area with horizontal lines. That's 0.985, that is nothing but Z less probability of Z less than 1.7, but we are looking at tail, so we are going to subtract it from 1. So for probability Z more than 2.17 is going to be 1 minus that particular value, 0.9850, and then we should be able to get that probability as 0.015. Now that is only this particular one tail, but we know that our hypothesis testing in this case is two-tailed hypothesis or two-sided hypothesis. So we have to double this value. Why double? Because it's a symmetrical curve, so whatever area will be on this particular same z value but positive will be having the same area for the negative value of same z score. So negative 2.17, you can think of that. So basically we are going to double that area. So that's why the actual p value will be 2 times that probability. So 2 times 0.015, that will give us 0.0. So that's how you get p value. And I want to hold it right now because I'm going to show you the alternative way. You don't have to do both. You can just go for one of them. So using table C instead of using table B, from the z-score 2.17, we just simply look for corresponding confidence interval. In this case, let's just look at 95% confidence interval. So let's just look at z of 2.17 using table C. So table C, This is table C, and we have the z-score at the bottom. So 2.17 would be somewhere in between these two values, 2.051, 054, and 2.326. And we can correspondingly look for one-sided or two-sided. We know our hypothesis testing is two-sided, so we are going to look at this corresponding um, two-sided p-value. So let me just show you. So z-score, look for corresponding lower bound and look for corresponding higher bound, because we know our desired z lies in between these two values. Right? So our desired two-sided p-value will also be within these two values. So just take the sum of them, 0.04 plus 0.02 divided by 2, and that will give us the approximate, not the exact, and that should be 0.03. So that's how we get the p-value as 0.03 for that part. So it's same as this step. Once you get the p-value by either of these methods, now you have to just compare the z-value with alpha. Right? So that is what we have stated here as steps. So let's look at 95% confidence interval, meaning that we are looking at significance level of 5%. 95% confident, we are 95% confident, that means 5% of time we are making some kind of error. 5%, 0.05, that's the alpha level. So we are comparing the p with that particular alpha level of significance. So we are comparing p with 0.05, and we can see that our p-value by calculation is 0.05. We are comparing that with 0.05, which is certainly less than 0.05. And whenever we have p less than or equal to alpha, or this significance level, we reject the null. And this is like the key conclusion part that you need to know. Whenever p is less than or equal to alpha, or that level in this case is 0.05, because we just preferred to go for 95. You can select whatever confidence interval you want to go for. But as a standard process, just go for 95% confidence interval unless another is specified in the question. So it's less than alpha, we reject null hypothesis. In other words, we favor alternative hypothesis, because if one is not true, other is going to be true, right? More likely to be true. Therefore, we reject the null hypothesis that mu is equal to 100, because our null hypothesis is mu equals to 100, and then we favor that mu is not equal to 100. Therefore, we favor alternative mu is not equal to 100. And that's our final answer for this.